Well, for solving this problem, we have invited once more Mr. Cauchy. So, Mr. Cauchy, we have a function f which is defined on the interval 0 and 1. And we know that the function f of 0 is equal to 1 and the function of 1 equals 2. Could you tell us, please, what kind of conditions would the guarantee that f prime c is equal to 1 for some, number between 0 and 1? Of course. I will be very pleased to work out this problem for you. So first of all, let me see what you know, right? Let me see here. What do we know about f? Well, you definitely would need a function, right? F, which is continuous on the closed interval 0, 1. You need a function f, which is differentiable on the open interval 0, 1. And also, what you're asking here is that, these conditions will guarantee, for instance, that plus what you're given here, the f of 0 is equal to 1 and f of 1 is equal to 2. Would you guarantee that f prime of c is equal to 1? Well, f prime of c, by my theorem, which is also called the mean value theorem. Please, mean does not mean that it's a mean theorem. It means that it's the average, don't forget. Okay, so f prime of c is equal to f of 1 minus f of 0 over 1 minus 0, which is the average. So it will be f of 1, 2 minus 1, 1. So it will be 1. Is that right? Yes. So as you can tell, because of the conditions that are given on the function, Mr. Cauchy, you sound a little bit Russian. Sometimes I also like to speak Russian. But anyway, we have a function f which is continuous, which is differentiable if that satisfies this condition. So for sure, we know there exists a point of prime of c such that will be equal to 1. So this, what I'm trying to say is that these conditions would tell us for sure that the function of prime of c will be equal to 1 for some number c between 0 and 1. So, therefore, what you just need is a function continuous, differentiable 0, 1. And if this function satisfies also these conditions, that you are saying f of 0 equals 1, f of 1 equals 2, you will be in a very good position. Okay, Mr. Cauchy, so you're saying that if you, for instance, you know that the function f is just continuous, and then f of 0 equals 1, f of 1 equals 2, could you say that f prime of c is equal to 1? What are you talking about? Not possible. You need the function to be differentiable in 0, 1. It must be differentiable in 0, 1. If you don't have that, you cannot guarantee. For instance, let me give you an example. For instance, look at this function here. Let's put it to be equal to 1 and to be equal to 2. Now, when I take the function to be sort of absolute value function, look at it. This function here is not differentiable at this point. Do you think that the derivative is anywhere between 0 and 1? Is the derivative anywhere from 0 to 1 equal to 1? Right? No way, it's not possible. So this is a case where this function is not differentiable at, for instance, x equals 1/2. So this doesn't property, mean value theorem doesn't work. Okay. And how about a function which is not continuous, Mr. Cauchy? Well, what are you talking about? If it's not continuous, forget about it. Of course, if it's not continuous on the closed interval, forget about it. You can't absolutely conclude my theorem, right? You can just come up with lots of different examples where these things cannot happen. Just, actually, you should do it. Okay, Cauchy, we'll do it. So, guys, try to find out an example where the function f of 0 is equal to 1, f of 1 is equal to 2, and yet the function is not going to have ever derivative equal to 1 at any point. So how about you choose a function that, you take it like this and then say that, that would be like a part of a parabola, and then somewhere the derivative will be equal to 1, and where the derivative is equal to 1, just define it at a different point, right? That would work. So, let's see if this is a closed dot. Okay, good. So guys, good luck with this exercise. You definitely can do it.